Utilizing LTspice IV waveform viewer to analyze a circuit and perform basic measurements is very useful. However, there are times when you need to evaluate a circuit with a numerical analysis. For these circumstances, dot measure statements can be very powerful in evaluating user-defined electrical quantities. For example, dot measure statements enable measurements like rise and fall time, time delay, average, RMS, min, max, and peak-to-peak measurements, the classic find x when y occurs, the very useful derivative and integral equations, and many more. Welcome to LTspice IV Evaluating Electrical Quantities video. I'm your host, Gabino Alonso. This video provides an introduction to using dot measure statements in performing numerical analysis of a circuit in LTspice IV. Since covering all the nuances of dot measure statements would make for a very long video, this presentation will focus on one example that provides a good overview. Here is an example simulation circuit based on the LT3798 isolated non-optocoupler flyback controller with active power factor correction. Since this design incorporates active power factor correction, I thought it would be interesting to use the dot measure statements to calculate the power factor. To calculate the power factor, we need to look at the input voltage source, V1, so let's focus on our attention to this part of the circuit. Recall that power factor is a dimensionless number between 0 and 1 that represents the amount of energy stored in the load and returned to the source. If the load was purely resistive, the power factor of the circuit would be 1. The voltage and current would be in phase. However, with nonlinear loads, the current drawn from the source can be distorted and the power factor can be less than 1. The voltage and current out of phase. The purpose of power factor correction is to counteract the distortion of nonlinear loads and raise the power factor so that it minimizes energy loss in a distribution system. Even though you're not familiar with power factor, how it's calculated, I hope you still can follow through this example and learn how to use dot measure statements. As we can see, V1 is a sinusoidal source with a particular amplitude and frequency. To plot the voltage on the waveform viewer, I can take my cursor to the positive side of the voltage source, click and hold, drag my cursor over to the negative side of the voltage source. You'll notice the voltage probe changed color, and then unclick. Likewise, if I wanted to plot on the waveform viewer the current generated by the voltage source, I can take my cursor, hover over the symbol for the voltage source, and you notice it changes now to a current probe. Please note the convention of current in this case is positive into the voltage source, and then I can plot that on the waveform viewer by clicking on the voltage source. We can now look at the waveform viewer and see these two waveforms side by side. Since the convention for current is positive into the source, I'm going to adjust the waveform viewer by right-clicking on the symbol for the current and adding a negative sign. Even though the waveform viewer shows us that the current and voltage are in phase, it does not provide us a method to calculate the actual power factor. To calculate the power factor, we're going to need to get the ratio of the real power to apparent power at the input voltage source V1. So let's go back to the schematic editor and let's take a look at some dot measure statements that I've already included that does this calculation. Since I already pasted a SPICE directive with a list of dot measure statements into the schematic, we can review it by right-clicking on the text to edit. To calculate the real power, we need to take the average of the instantaneous power over a period of time. That is defined by this dot measure statement. This dot measure statement takes the average of V times I of the input source over a time range of interest. Recall that current direction of the voltage source is positive into the symbol, so I've adjusted this statement with a negative sign so the result is positive. Additionally, the start and end are defined in the previous two dot measure statements as 30 milliseconds and 40 milliseconds. Apparent power is the absolute value of the complex power, which is the product of the root mean squared of the voltage and current. To perform this calculation, I have included individual dot measure statements to calculate VRMS and IRMS over a period of time, and then use those results to calculate the apparent power. Please note that to use the prior results of VRMS and IRMS in the subsequent apparent power calculation, the param keyword needs to be included in the dot measure statement. Finally, we can take the ratio of real power to apparent power to calculate the overall power factor. Since dot measure statements are done in post-processing after the simulation is completed, the accuracy of the numerical analysis is limited by the accuracy of the waveform data after compression. Therefore, to adjust the optimal data collection in the simulation, I've added two statements at the top of this SPICE directive. The first one disables compression and defines double precision for the data. The second limits the data collection to only those nodes that are of interest for the numerical calculation. In this case, the voltage and the current of the input source. You can explore further options by looking at the LTspice help files with regard to .options and .save. To close the text editor, we can either select OK or Cancel. We can now select the running man on the toolbar to execute our simulation, and I've already done this previously. Once the simulation is complete, the output of these .measure statements that we've included in our schematic will be inserted into the SPICE error log file. To view the error file, you can use the menu command View, SPICE error log, and scroll through this error log file until you come across the results of your .measure statement. From our calculation, we can see my initial design has a power factor of 0.98 on average, and that gives me a really good starting point to explore further optimization of my design. As you can see, .measure statements can be a very powerful tool in simulations, and I encourage LTspice users to learn more about this command and others using the LTspice IV help files. For more information or to download LTspice for free, please visit us at www.linear.com/LTspice. Happy simulations.